What I'd like to do today is present a thought experiment on basically discriminating between different mechanisms by which sediments may be entrained into the deep continental crust. So interest in the topic is motivated by observations like this, that metasediments, specifically perluminous metasediments, are common constituents of high-grade metamorphic terranes. Here's one such example. So this is a picture from Valmolenco in the Italian Alps. And what we see here and in many other granulite-facies terranes is the close association of perluminous, in this case garnet, kyanite, biotite, beautiful rutilated quartz, and really close associated with mantle rocks. So here we have peritites. This is a Veriscan age section, of course, within meters of something that used to be a shale normally. Okay, the question then is, how does it get down there? Why is this important? Well, two reasons. Firstly, the available seismic, heat flow, and compositional constraints suggest that there may be significant proportions of this type of material in the lower crust, coming from work from Brad Hacker in 2015. Another reason is that such rock shales, sediments tend to dominate heat productivity in the deep crust. So shown here, these are quantiles of heat production rates from Hasbrock's compilation. And these are plutonic rocks in blue. And these are the common clastic sediments, shales and greywackies. And they tend to dominate the heat production, with the exception, of course, of granite, many of which granites we know S-types come from the melting of sediments. What are the implications thermally? Here's just an example calculation showing the implications of different depth distributions of nominal sediments in the deep crust. And you can see that depending on whereabouts the sediments are buried, there are hidden parameters here with depth of thrusting, etc. But the point is, depending on the distribution of the radiogenic heat production, could lead to several hundred degrees C difference in the geothermal depth. Typically, or generally, the deeper the heat production is, the larger the effect on the geotherm. And this is going to have significant consequences on the rheological structure of the continental crust. So how do these things get down there? As I see it, there are four main ways of doing this. First of which is really contraction. So lower crustal underplating. This has been seismically imaged along many subduction zones whereby material is underplated from a downgoing plate to the base of the overlying plate. The cartoon sketch of PT paths here. The aim is to show relative differences in the PT paths for each mechanism here. We might expect concomitant burial and heating on the way to the lower crust. Burial. So just overplating of magmatic material by sediments leads to potential isothermal compression, as has been noted along the coastal plutonic complex by Brown and Walker. The rate of loading to the rate of temperature increase during loading is going to be controlled by the dynamics of the system, of course. Back arc under thrusting, whereby contraction, deformation is accommodated behind the arc, is another mechanism by which sediments have been thought to be entrained below crust by Stacia Gordon and colleagues along the northern Cascades. Special emphasis here is relamination. So the relamination mechanism involves subduction of sediments and growth of Rayleigh-Taylor type instabilities in response to low viscosity, low density sediments on top of the plate. They rise to the mantle wedge and then become entrained in the deep crust. Relative to the other mechanisms, we might expect a rock that has found its way or ended up in the lower crust via relamination to have experienced higher pressures, and what I'm going to focus on here is higher temperatures. At least some part of the relaminant must have experienced ambient temperatures of the mantle wedge. Why is this important? Well, mechanism 4 here, relamination compared to the other mechanisms, implies that there is a net change to the mass of the crust, because the melting and the differentiation, at least some part of it, occurs in the mantle wedge. So, honing in on relamination, I'm trying to design a test here of what we might look for as a sign of a rock that's been relaminated. I want to emphasize the fact that at least some portion of a rising diapir from a downgoing slab would be expected to have experienced the ambient temperatures of the mantle wedge. This paper by Zhang nicely illustrates this fact. So here's a diapir, the thermal field through a rising diapir through the mantle wedge. And you can see that the colors on the outside here are red. That's the ambient mantle temperature. So do perluminous, specifically perluminous, for the ease of identifying such rocks in the global lower crustal rock record, do perluminous lower crustal metasediments preserve compositions that are consistent with ultra-high temperature interactions of the mantle wedge? That's going to be the focus of the remaining slides here. In order to look at the big compilation of rocks from granulite-facies, terranes, and xenoliths and test this hypothesis, I want to first turn to the Evrea zone. It seems like all roads lead to the Evrea zone. Why are we doing this? What does a UHT perluminous metasediment actually look like? I'm not emphasizing or proposing that these rocks are relaminates, rather using this as a case study to demonstrate the geochemical characteristics of UHT metasediments. And I'm not going to give a background to the Evrea zone, I feel that's been done already. But what I want to do is focus on some small slivers of the peelites that have spalled off into the mafic complex, the septa. Okay, and these are strongly restitic peelites, is that they look like in the outcrop. Beautiful rocks, very garnet, selimanite rich, prismatic selimanite. But critically, they've experienced or thermally equilibrated with nominally basaltic melt at around 1200 degrees C. So they fell off and were incorporated and immersed in that basaltic melt. Folks, including Pape and Tanya Ewing, have worked on the 4+ thermometry and shown that the temperatures they preserve are consistent with equilibration at mantle wedge tidal temperatures. So what are the mineralogical and the bulk rock characteristics of these rocks, and can we use that to identify potential relaminates in the lower crust? This is what the rocks look like in plain polars. Beautiful things. Seams of strongly restitic mineralogy, up to 50% garnet with prismatic selimanite. The rutile are incredibly euhedral, up to 1 millimeter long. Ternary feldspar and quartz dominate variable amounts of leucosome. And a key observation is the accessory phases. So subordinate zircon, but the matrix, there's no matrix monazite. And that's a key observation here that controls the bulk rock characteristics, certainly the trace elements. This is a set of backscatter images showing that actually some of the peritectic garnet does actually include some specular micro-sized monazite. But the key thing is there's no monazite in the matrix. These rocks all been dissolved. Okay, so bulk rock geochemistry of the UHT septa. First off, I'm presenting bulk rock analyses normalized to average upper continental crust of the protoliths of the septa. Shown in green here, this is these are bulk rock data normalized to upper crust composition of Rudnick and Gow for amphibolite-facies, peelites along the Evrea zone, and granulite-facies. I wish to emphasize that there's very little change. Depletion in the large iron lithophiles and nominally a small amount in uranium, but they're reasonably similar. However, if we include the septa here, really we get an idea of what the effect of UHT temperatures does to these rocks at the bulk rock scale. There are 3 traits I want to emphasize. The first of which falls on that observation I just emphasized, that there's no monazite in the matrix. So these rocks, the septa, are depleted in thorium, massively depleted in thorium, relative to the amphibolite protolith, as well as the light rare earths and phosphorus. Again, consistent with the dissolution of monazite. Also enriched in the high field strength elements, consistent with the growth of a large amount of rutile through the progressive breakdown of high titanium biotite stabilization of a large amount of rutile. And as we'd expect, based on the mineralogy, an enrichment in the trace elements that go into garnet as well. Okay, so wish to emphasize that rutile in particular, if you look at the titanium here, you see the concentration of titanium gradually increases from amphibolite to granulite to the UHT septa. If we assume conservative or immobile behavior of titanium, I'm able to quantify the mass change for each of these elements based on conservation of titanium. So this is what I'm showing you here, the mass change for the granulites relative to an amphibolite precursor, and the UHT septa relative to the amphibolite protolith. And again, the dissolution of monazite leads to a depletion of thorium, as well as a depletion of the light rare earths, an enrichment in the high field strength elements, according to the growth of, explained by the growth of rutile, as well as an enrichment in garnet. With some reasonable assumptions in terms of the bulk rock density, it's possible to convert these mass changes to volume strain. And what I'm showing here on the right is estimates of volume strain for both the UHT septa in red and the granulites, so restitic granulites in blue. And what we see is two things. Firstly, that there is a trend in volume strain, i.e. melt loss, with SiO2, which is what we expect, depending on how much leucosome has been removed. But the interesting thing is, even the most restitic granulites have lost roughly the same amount of melt as the UHT septa. Okay, that's interesting because it provides a conundrum in terms of why is the monazite gone? Okay, the dissolution of monazite under UHT conditions is huge implications for the heat production throughout the continental crust. Shown here is the work of Alessio. In 2018, they measured heat production along the Abrea zone, really nice study. And they made the point that really the heat production was conserved independent of grade. So the top panel here, this is thorium concentration down the Abrea zone from sub to suprasolidus. I've superimposed the UHT septa here, okay, and rough temperatures, peak temperatures. And look at the step function here. So really, monazite is conserved, it's recrystallized right the way up until the UHT conditions, but it's not been dissolved. It's this final temperature increase that seems to be significantly important, or all important, for the dissolution of monazite. Why is this the case? I can't answer that in this talk, but it doesn't seem to be related to equilibrium partitioning with melt. Why is that? Well, superimposed here is the solubility of monazite in silicate melt from Stepanov experiments, and there's no indication of an exponential decrease in either thorium or the heat production here. Okay, so back to the initial task of using these rocks as really a demonstration of what we might look for in a bulk rock scale to identify a reed laminate, or a rock that's interactive with the mantle. Well, the titanium-thorium ratio seems to do a good job at this. So I'm showing you here bulk rock titanium thorium for the septa, the granulite-facies, and the amphibolite-facies rocks from the Abrea zone, plotted against thorium. And there are two trends, or two parts of the I want to explain. The first is that the septa, the most restitic septa, have very high titanium thorium, okay, at low values of thorium, whereas the granulite-facies and the amphibolite-facies rocks have low titanium thorium to high thorium values. So the other thing is that there is a large tail that spreads to high thorium values, and we can correlate this with the amount of melt extraction. Okay, so this is basically explained by the amount of melt that's been trapped, the SiO2 value of the bulk rock. Do rocks where independent PT constraints exist and are consistent with the predictions of relamination, i.e. high pressures and high temperatures, do they have elevated titanium thorium? Well, Kochetav and the Bohemian Massive, they tend to do that. Okay, so they all each have elevated titanium thorium. Again, they show this this tail out to high thorium values consistent with inefficient melt extraction. But at least the maximum values of titanium thorium is consistent with the indication from the Abrea zone. Okay, wild speculation. This is a compilation of around 40 or so lower crustal rock suites. So perluminous metasediments from granulite-facies terranes and xenoliths. And it's showing the same plot, so titanium thorium versus thorium. the maximum values of titanium thorium from these perluminous sediments, for the majority of rocks in the lower crust here, are inconsistent with that high range of titanium thorium derived from the UHT sector in the Abrea zone. So this doesn't, as much as we can infer a tectonic process from a bulk rock ratio, doesn't discriminate from relamination. But what it does say, or allow us to say, is that certainly the maximum values of titanium thorium for the majority of these lower crustal rocks are inconsistent with interactions with the mantle wedge. Okay, conclusions. So monazite dissolution and enrichment in the high field strength elements seems to be characteristic for perluminous UHT restites. High bulk rock over 1,000 for UHT perluminous metasediments. It's disproportionately important for the mobilization of heat-producing elements, which can have long-lasting implications for the structure, the thermal structure of the crust. Prospective relaminants should have, or expected to have, high titanium thorium, yet the majority of xenoliths and low exhumed terranes have low titanium thorium. And the speculation here that certainly requires a lot of follow-up work from different angles is that intracrustal recycling of sediments, mechanisms 1 through 3 in the introduction, would seem to be more prevalent in the burial and entrainment of perluminous material into the deep crust than the relamination. Thanks for listening.
Well, Andy, that was great, thank you. Just a question, okay, so at UHT, obviously these heat-producing elements are no longer in the terraluminous rocks, but they must have gone somewhere.
Yeah.
So does that mean that they've been basically incorporated in the basaltic rocks or the mantle that have then moved the relaminates, if you want to know? And if so, then those heat-producing elements are still there and they're still in the lower crust, just not in the rocks that expect them to be?
Well, I think certainly in the mafic complex, there's isotopic evidence for hybridization of the basalt close to the sector. So I suspect in the mafic complex, that metal is just intermingled with the basalt. In the mantle wedge, we'd expect it to react. Yeah.
Just one more question. Sticks. Look first.
Okay. Yeah, we talk about the idea that a lot of these so-called lower crustal rocks are in fact not, and they're actually mid-orogenic crust. You know, a lot of these areas have another 25, 30 years under them. But actually, they're not really lower crust. They're actually middle crust.
Yeah, I mean, that's an interesting. Yeah, that's an interesting question. How do you define a lower crustal rock? I mean, even I'm not showing it here, but even if you look at rocks that would satisfy a more stringent range of PTT constraints, i.e., they've resided for hundreds of million years at lower crustal PT, these trends seem to exist. So, yeah, it's a fair point. Maybe we need to extend this to look at other rocks. Yeah. Sure.